This resource is the third in a 5-part series on vectors. Part 1 defines vectors. The component form for a position vector is presented with an example. We also discover how to find the magnitude of a vector. Part 2 considers basic operations with vectors. We look at adding and subtracting vectors in component form with examples. We also consider scalar multiplication of vectors. Part 3 considers writing the vector in terms of its magnitude and direction. Part 4 describes how to find the resultant force when two different forces act on the same object. Part 5 looks at the dot product of two vectors, looking at multiple examples, including a word problem. A vector can be described in terms much like an angle can be written in polar coordinates. Polar coordinates measure a distance and an angle from the positive x direction. This is exactly another method for defining a vector, in terms of its magnitude, its length, and theta, the direction angle, which is the angle between the vector and the positive x-axis. Depending on how the angle is described, we may have to redefine it to ensure a proper direction angle. The graphs show how to do this definition. If the angle A is in the second quadrant, theta equals 180 degrees minus the measure of A. If the angle A is in the third quadrant, theta equals 180 degrees plus the measure of A. If the angle A is in the fourth quadrant, theta equals 360 degrees minus the measure of angle A. But how can we take this information and develop our position vector? Suppose we know the magnitude and the direction angle theta. The x direction component is the magnitude multiplied by the cosine of theta. The y direction component is the magnitude multiplied by the sine of theta. This transformation is very useful in physics and real-world problems, as forces are usually described by their magnitude and their direction, rather than broken down into their directional components. Let's look at a couple of examples. Suppose we have a vector with a magnitude of 20 and a directional angle of 60 degrees. What is the position vector notation for this vector? We plug this information into the formula described earlier. This gives us the position vector of 10i plus 17.32 j. What about a more realistic, real-world example? Suppose we know that a car has a velocity of 50 miles per hour, traveling a direction 30 degrees north of west. What is this velocity when written as a position vector? First, we have to redefine our angle. North of west means that we are in the second quadrant, so we subtract the given angle from 180. This means our direction angle theta is 150 degrees. Now we can plug our information into the formula. This gives us the position vector v equal to negative 43.3 I plus 25j.